Hi, my name is Curry Caputo, and I'm a partner in Sustainable Structures. We are an energy efficiency and energy auditing service company. We also do new construction of green buildings. We are here today at the Christian Science Church in Damariscotta doing an energy audit of the building to find out where we can save these folks some energy. We're looking at the air barrier today to see how leaky the building is. We're looking at the thermal boundary to see how effective the insulation is, and we're also doing some combustion safety testing to determine how efficiently and how safe the heating system operates. What we will see in this church today is typical of most buildings in the state of Maine. This is not a very large church. The construction types, the framing type is very similar to a lot of buildings we see. And we can transfer whatever we see with homes into these spaces that are sort of dual use. This doorway opens out. Most doors open in, but I think we can do this. Okay, and this reference hose gives us a reference to outdoor pressures. Okay, now the blower sits in this opening. Called a digital manometer. It's used to measure pressure differentials. And we'll hook up some hoses, one hose to the fan and one hose to our reference line, which goes outside. Tom's just going into the basement to shut off the combustion appliance because as we depressurize the house, not only will air be drawn in all of the collective nooks, cracks, and crannies, but it'll also be pulled down the chimney flue. So we need to turn off that furnace to make sure that it doesn't inadvertently come on and backdraft flue gases into our environment. Jamie and I have already gone around and checked that all of the exterior windows are closed and locked. What we want to do is create wintertime conditions for the building. Then we'll start the depressurization and find out immediately how much air is flowing through the building at our imposed pressure. And then we can do some quick math to determine the number of square inches of leak space in the building. So now the fan is ready to turn on, and we'll fire it up and see what we have for leakage. So we'll give that a chance to do some averaging, and then we'll be able to determine the amount of air that's flowing through this fan at the imposed pressure and what that translates to in square inches of leak space. So right now I'm reading off the pressure gauge. We have 2,815 cubic feet a minute traveling through this fan at our imposed pressure. A cubic foot is roughly the size of a basketball, so we have 2,800 basketballs worth of air every minute flowing through this fan. Once we calculate the volume of the building and use some other factors, we'll be able to compare this imposed airflow to energy efficiency guidelines and ventilation guidelines to tell whether we are over-ventilated or under-ventilated. We suspect that the building is probably over-ventilated just given its age and the materials that we've seen so far. But once we do that calculation, we'll be able to more accurately tell where the building rates. So I'm going to put down our airflow number now. We are at 2,823 cubic feet a minute. And if we divide this number by 10, that gives us the square inches of leak space. So there's roughly 282 square inches of leak space. And if I get out my calculator here and do a square root on that number, 282 square rooted gives us a square opening 16 3/4 inches by 16 3/4 inches. This is the window that's open all the time in this building. So it's there's given that the building is not very large, it's a sizable amount of airflow that's going through here. So as we go through with our infrared and accurately depict the exterior surfaces and where this air leakage is occurring, we're going to keep that 16 3/4 by 16 3/4 number in mind and try to find all of those leaks. So what we have here, again, is the south elevation of the church. We have the vertical high-posted wall coming into the plane of the sloped ceiling. The infrared camera gives us a color rendered picture of the surface temperatures that we are detecting. The blue is the colder and the red is the warmer surface. So what we're able to see is that there's a significant amount of airflow occurring through that sloped ceiling. Likely the cause is air being pulled from the attic space down into the slope, or vice versa, air being pulled up through the soffits up through those sloped areas. I can tell right away that there is fiberglass in these areas, and we'll do a little bit of research in the attic to corroborate that. We can also see that between these two windows, you can see the stud bays now. You have some studs here. And there is also quite a temperature gradient occurring within the stud bays, which again suggests to me that there's a very poor air barrier in those stud bays. Air is allowed to flow through those cavities. Anytime there's air flowing around, bypassing, or through insulation, it basically destroys the R value of that insulation. This is also interesting because we have airflow occurring through an interior partition. This interior partition, which is in front of the altar area, is communicating with the attic right now. So there's air being pulled from the attic, and it's leaking into these interior partition stud bays. And we'll get a smoke generator out later to visualize some of the airflow that's occurring. But we'll find air being pulled from the attic and then exiting out outlets, door and window casing, baseboards, any place there's a penetration in these interior partitions is going to feed that airflow. This is a non-toxic smoke generator. It looks like a kid's toy because it is a kid's toy. This is a glycol-based theatrical smoke. And what it allows us to do is to get a visual on airflow through the building. This is a really good example of air leakage. You can see these fingers of cold air coming out from underneath that attic hatch. This attic hatch is just a piece of plywood sitting on a stop, so there's no gasket to prevent airflow from occurring. So what we'll do, now that I've seen it on the infrared, I can go back with the smoke generator and get a good sense of the amount of smoke that's coming through here, amount of air that's flowing through. This one's not working real well right now. Can you see that blowing across there? The smoke blows right across. So this is just a way for us to corroborate what we believe we're seeing with the infrared camera. So a prescription for this would be to install a gasket, a foam rubber gasket, between the stop and the attic hatch, and then we would put a closure hardware on here to compress that gasket. Once we've done that, we've stopped airflow through these air breaches. So we'll just continue around and try to find some more air barrier leak sites here. We've been into the attic already, so we have an idea of what's going on up here, but you can see a marked difference in this interior partition. You can see this is an interior wall, very warm in this area. As you move up towards the top of the wall where it intersects the flat attic ceiling, it's completely cold. And what we from the attic have found is that there's a flat ceiling and it drops, there's a drop, and then a lower flat ceiling on either end of the building. So what we found is that there's basically no insulation in that upper part of the wall, and air is washing over the drywall on the back side of it, essentially just whisking heat away under normal conditions. So we are trained to go to the attic first. There's always, as far as energy savings, the attic is the most likely place that you're going to find air barrier breaches as well as inferior insulation. If we can tighten the top of the building, get a good thermal boundary in the top of the building, then you're going to save an amazing amount of energy. Then we're trained to go to the basement. We want to short circuit airflow. So you can short circuit at the top by preventing the air from escaping. It slows down infiltration at lower levels. Likewise, if we can short circuit airflow from the basement, it's going to disallow air flow through the building from its source. So we go to the top, then we go to the bottom, and we work in between. Attics are a great place to start because you can do work there. These exterior surfaces here, these walls, if there is insulation in them, becomes very difficult to retrofit because it becomes invasive. You have to take off the sheetrock. You have to take out the insulation that's there and replace it. If these stud cavities were completely open with no insulation, it would make my job a lot easier because I can prescribe a dense packed cellulose insulation to go into these cavities and completely fill them on a very long-term basis. So oftentimes we like to see no insulation in houses because then we can offer really tremendous energy savings to the customer. And the retrofitability becomes easier. Attics, a lot of access, very easy to get up there, very easy to fix what's going on. Walls, not so easy. Basements, a little easier. So we will come up with a prescription for all of these exterior surfaces, a prioritized list of retrofits. So if you have money to spend now on your building, spend it on, A, B, and C. If your money is available down the road and you want to do further energy savings measures, then you'll do some of the moderate priorities. And then there's always the last 5 or 10% that some customers really want to tune their building that they'll tackle those. Those are typically window replacements, caulking, baseboards, exposed beam work, things like that where there is a small amount of airflow occurring that doesn't really impact energy efficiency greatly, but it can be a comfort issue. If you're sitting at a couch and your head, and behind you is a leaky window, while it might not be a serious energy draw in your house, it's a comfort issue. You're not going to want a draft at the back of your head, and we know you can't put a price on comfort. So a lot of people are surprised to hear that window replacement is really low on the list, and in the dozens and dozens of audits that I've done, I've recommended window replacement twice. So it's really, we have building modeling software that we use, and we've found that the payback for window replacement can be 50, 75, 100 years. You'll never get the money back out of it in energy savings that you put in for replacing the windows. Attic insulation, payback can be 2 years, 3 years, 5 years, up to 10 years. So it's a really good return on your investment. In fact, better than the stock market, I can say pretty easily right now. So what we're going to do now is what we call a worst-case depressurization test. What we need to find out is what we look at is the base pressure difference between the outside of the building and the inside of the building. That gives us a groundwork to start from. And then what we do is we create a worst-case condition for the building. And in buildings, what that typically means is turning on all of the exhaust appliances, like I mentioned before, bathroom exhaust fans, range hoods, dryers, anything that takes indoor air and exhausts it outside deprives the heating system of necessary combustion air. So what we'll do is we'll get a baseline reading, pressure difference inside and outside. Then, since this building does not have exhaust appliances, the only other thing which may affect pressure in this combustion appliance zone is the actual blower for the furnace. So what we'll do is we will replace the panel that covers this combustion appliance zone. We will turn on the air handler for the furnace, and then we'll look at how much depressurization happens in that combustion appliance zone. If there is an inordinate amount of depressurization, which means a sucking basically effect, then we could have backdrafting or we could have spillage on startup of the combustion appliance. Okay, so now the fan is operating. Sounds like there's a squealing belt a little bit, maybe. But the combustion appliance has not come on, so now we can look at how this is affecting the building pressures. So we've depressurized by 1 pascal. The limit for a furnace such as this is -5 pascals. So if we had seen this -1.4 jump up to a -6.4, -7, then we'd know we have a depressurization problem. And like Tom said, we could potentially have backdrafting or spillage of flue gases on startup. So we passed the test. We've determined that under worst case conditions, the heater will operate safely. The next thing we will do is we'll actually start the combustion appliance. During the first minute of startup, we're going to try to determine whether or not flue gases are spilling out of the barometric draft controller. The barometric draft controller is an inline pipe. I'm sure you've seen them with a little weight-actuated door. And what that door allows is for the dilution of flue gases. It adds air to the flue gas to allow a stronger draft. So what we'll do is we'll try to determine whether any flue gases are backdrafting out of that barometric draft controller during the first 60 seconds. If they do, we have guidelines we go by to determine whether or not it's an actionable item. Do we have to recommend that this be fixed before we do any air tightening measures? Because if there's this pre-existing problem, it will certainly get worse. We'll drill a hole here that we can test the flue gases in. So what we'll do is we'll get the smoke going here. Tom will start the combustion appliance. Go for it. I want to see that this smoke is being drawn in the flue. I don't see it backdrafting out of the barometric draft controller, which means that it is being drawn in and up the chimney, so we don't have what we call spillage. I'm gonna count out basically 60 seconds to make sure that during this first minute we don't have spillage occurring, and if in fact it doesn't start to spill, then we've passed the spillage test. We're looking good here. We have no spillage occurring on startup. That's one of the test procedures that we need to be certain of. So, we'll stick our probe in our test hole, perpendicular to flow, about halfway into the flue itself, and immediately we'll start to get some diagnostic numbers here. And right now, it's calculating efficiency based upon the composition of the flue gases, and you can see the efficiency reading is slowly going down as the temperature rises. Right now it's roughly 82% efficiency. And if I scroll through these screens, I'm able to see the parts per million of carbon monoxide. We're currently at 15 parts per million, which is below the safety threshold. If we detected parts per million of 25 or greater, then it would be what we call actionable, and we would have to come up with a recommendation to remedy that problem. This lower number is the percentage of oxygen in the flue gas. We have the amount of carbon dioxide and the amount of excess air being pulled through the system. At first blush, what I'm seeing is higher than normal levels of oxygen at around 9%. We'd like to see it between 4 and 7%. And I'm seeing lower than expected percentage of carbon dioxide. Carbon dioxide is a byproduct of complete combustion. We would like to see 12 to 13% carbon dioxide. And then the last number that I'm concerned with is this excess air. This is the percent of air that is traveling through the combustion chamber and not being used for combustion. So what that means is what we want to see is about 25% maximum of excess air. So there's a lot of air being taken through the combustion chamber, not being used for combustion, and all that's doing is carrying heat out the chimney. This again is a digital manometer. It measures pressure in pascals. So what I'll do is probe, and this is telling how much pressure is forcing the air out, or the flue gases out of the chimney. Right now we're seeing a draft value of roughly negative 11 pascals. It's certainly within what we call the acceptable range for draft values, so I don't see a problem with draft in this appliance at all. I will hold those numbers and then record them, and generally speaking, this combustion appliance passed the test. We don't have any safety concerns with it. There are some efficiency concerns, but those won't necessarily translate into a dangerous situation. But we're certainly going to recommend that a licensed heating technician come and do another test on this system and try to decrease the amount of excess air going through the combustion process, try to raise the carbon dioxide levels and lower the oxygen levels. So now that this combustion appliance has been running, we want to make sure that there's no carbon monoxide in the surrounding areas. So I'll just get the gas to sample. We're getting the air blowing by the sampling tube, and I'm seeing that the parts per million is staying stable at 0, so we don't have a problem with the cracked heater exchanger. Just walking around this area, looking to see if we've got any carbon monoxide in the ambient air, and I don't. So we're again at 0 parts per million. So we have a safe situation here with this combustion appliance, and that's reassuring considering the number of people that use the space. The worse the news is, the more you have to gain. If your house is horrid for air sealing, for insulation, or for combustion safety, then you're going to gain a lot of efficiency and you're going to save a lot of money by doing these retrofits. And the litmus test that I give to customers when we first talk about whether or not to do a home performance analysis is if you have a sense that your building is inefficient, then it probably is.